So, hello and welcome to our ninth lesson in our study of optimization 2. So, in this video, we will talk about types of linear programming solutions and also talk about tiebreaker analysis. Okay, so when we solve a linear programming model, we can have some kind of solution. So, we'll talk about those scenarios. Then, when you are performing our iterations, there can be a tie, right, for the entering and leaving basis. So when there is a tie, how do we go about it? So that's what we seek to address in this video. So let's look at when there is a tie for entering basic variable. All right, that's the key column. So when you are solving um when you are doing an iteration, right? So for instance, with this iteration, when we got here, we're trying to maximize. That means that the optimal solution was for all the cj minus zj's to be less than or equal to 0. Okay, so here we had just 13 over 7, right? So because this is positive, it entered into the basis to take away s2. So what if we had 13 over 7 here, and we also had, let's say, 13 over 7 here? So which of the two is supposed to go in? Alright, so that's the kind of problem we seek to address here. So while solving a linear programming problem using simplex method, two or more columns of simplex table may have the same cj minus zj value, positive or negative, depending upon the type of LP problem. So depending on whether we are maximizing or minimizing. So in order to break this tie, the selection for key column, that's the entering variable, can be made arbitrary. However, the number of iterations required to arrive at the optimal solution can be minimized by adopting the following rules. So that means that if there is a tie, you can select any of them arbitrarily to enter. But sometimes, depending on which one you select, you would have to do more iterations or do lesser iterations, right? So we have some rules to guide you to make the best decision, which will reduce the number of iterations you do. Okay, so the first one is that if there is a tie between two decision variables, and I hope you know what decision variables are, the variables in the objective function, right? So if there is a tie between two decision variables, then the selection can be made arbitrarily, right? So that means that if the decision variable, then you can choose any of them to enter, and you still get your optimal solution at the end. But if there is a tie between a decision variable and a slack or surplus variable, then select the decision variable to enter, right? This is self-explanatory. And if there is a tie between two slack or surplus variables, then the selection can be made arbitrarily. Okay, so these are some rules to guide you when there is a tie for the entering basic variable. Okay, so what if there is a tie for the leaving basic variable, right? The key rule. So this is the problem we call degeneracy. Okay, so while solving an LP problem, so okay, this is the, let me illustrate it here for you. So you see with this simplex tableau that we have here, let me use it to explain. Okay, so you see when we found the minimum ratio test, when we performed the minimum ratio test, we had 14 on 3 here, and we're getting a negative value here, so we brought dash. So now what if we had 14 on 3 here, and we also had 14 on 3 here? Now they all have the same value, but one of them is supposed to leave. So which of them should we choose to leave? Okay, and that's the kind of problem we are trying to address here. So while solving an LP problem, a situation may arise where either the minimum ratio to identify the basic variable to leave the basis is not unique, or value of one or more basic variable in the SB, that's the right hand side, becomes 0. So this causes the problem of degeneracy. So usually the problem of degeneracy arises due to redundant constraints. That is, one or more of the constraints of LP problem are not part of feasible solution space. Okay. So for example, consider this problem here. Constraint here where we have x1 to be less than or equal to 5, x2 to be less than or equal to 5 as well, and x1 plus x2 to be less than or equal to 5 in the LP problem. So you could see that since our first constraint is s1 is less than or equal to 5 and s2 is less than or equal to 5, this constraint s1 plus x2 less than or equal to 5 becomes redundant or unnecessary, because what if x1 is 4 and x2 is 4? You see that it becomes unnecessary to have this constraint, right? So mostly that issue arises when one or more of our constraints are redundant. So degeneracy may occur at any iteration of the simplex method, and in order to break the tie in the minimum ratios, the selection can be made arbitrarily. Okay, so however, the number of iterations required to arrive at the optimal solution can be minimized by adopting the following rules. So we will divide the coefficients of the slack variables in a simplex table where degeneracy is seen by the corresponding positive numbers of the key column in the row starting from left to right. Okay, and we compare the ratios in step 1 from left to right column wise. So we select the row that contains the smallest ratio, right? So when there is a tie between a slack and artificial variable to leave the basis, preference should be given to the artificial variable for leaving the basis. Okay, so this is when we do this when we have two decision variables leaving the basis. Okay, all right. So now let's go move on to types of solutions. So I said when we solve an LP problem using a simplex, we can have three types of solution, right? So we can have what we call the alternative or multiple optimal solution, unbounded solution, and infeasible solution, right? So with the alternate or multiple optimal solution, it means that we have been able to find an optimal solution to the problem, but the solution is, we can have an alternate solution to that solution, or we can have multiple solutions to that problem. Okay, so when you are performing your iteration, the cj minus zj values in a simplex table indicate the contribution in the objective function value by each unit of a variable choosing to enter into the basis. So we can talk about the shadow prices when you're talking about duality. Okay. So also an optimal solution to a maximization LP problem is reached when this condition holds. But if cj minus zj equals 0 for a non-basic variable column in the optimal solution table, and such non-basic variable is chosen to enter into the basis, then another optimal solution will show no improvement in the value of the objective function. Okay, so what this means is that you um so let's say we have a simplex table here, right? So I'm using this to explain to you. Okay, all right. So this is an optimal solution because we are maximizing, and all our cj minus zj are less than or equal to 0. Okay, all right. So you can see that x3 here is a basic variable, and the cj minus zj value is 0. And that is perfect because it has to be so. Then x1 prime is also a basic variable here, and its cj minus zj value is 0, which is perfect. But you can see that s1 prime prime is a non-basic variable, right? But its Cj minus Zj value is 0. That's what we can see here. So it means that with this problem, we can have a multiple solution or an alternate solution. And if we should let this S1 prime prime enter the basis, right? The truth is that the solution that we'll get is not going to cause any improvement in the objective function. So we call such a solution an alternate solution, right? Or a multiple solution. So that's what we mean by a multiple solution or alternate solution. Okay. Then let's go to unbounded solution. So in a maximization LP problem, if Cj minus Zj is greater than 0, or if Cj minus Zj is less than 0 for a maximization case, that corresponds to a non-basic variable in a simplex table, and all Aij values in this column are negative value in denominator. It will indicate the entry of a non-basic variable in a basis with a negative value. So also a zero value in the denominator would result in a ratio having an infinite value and would indicate that the value of non-basic variable will be increased infinitely with any of the current basic variables being removed from the basis. Okay. Alright, so what we mean by having an unbounded solution is that there are some of the solutions that when you get, you can increase them and they can increase infinitely or decrease infinitely. Okay, so when such a scenario occurs, then we say that that solution is unbounded, right? It doesn't have any bound. So that's what we mean by having an LP solution to an LP problem which is unbounded. So now let's talk about the last one. So infeasible solution. So if LP problem solution does not satisfy all of the constraints, then such a solution is called infeasible solution. Also, infeasible solution occurs when all Cj minus Zj values satisfy optimal solution condition, but at least one of the artificial variables appearing in the basis with a positive value. So we talked about this when we were talking about the two-phase method. Okay. So this situation may occur when an LP model is either improperly formulated or more than two of the constraints are incompatible. Okay, incompatible. So thank you very much. That's all for this video. I hope you learned something, right? So to gain a better understanding of what we just did, I'll advise you to read wide. Okay, so this brings the curtain to our LP model that we've been studying. So in our next series of videos, we are going to learn how to apply the LP models. Okay, and we are going to begin with transportation problems. So in our next video, that is lesson 10, we will introduce you to the transportation problem. Okay, so thank you very much and see you in the next lesson.